In this example, we are going to grow trees. It's a classification problem, and we are going to use a classification tree and see how it goes. So we have an online game app development company, and they want to be able to predict which games are likely to make up purchases. So we have data contains variables. The variables are the customer age, sex, income, number of years playing online games, number of hours playing online games per week, and whether the customer has a credit card, whether the customer has a Facebook profile, and whether the customer has made in-app purchases before, which is the buy. And we are going to create a classification tree model for predicting whether the customer will make in-app purchases. So this is my response variable, which is the buy. After that, the whole idea is to build the tree and select the best pruned tree for scoring and display, or for scoring a new data, or for just scoring a new data. We will be displaying the full-grown tree, the best pruned tree, and the minimum errors trees. I mean, 3 trees, maybe 2, because the minimum error sometimes is the same as the best pruned tree. So we are going to answer all these questions, and answering these questions is going to be the typical way of solving such problems. Okay. So these are the libraries that I need. Some of them, they are installed before. We have installed them. Some of them, they are not. Like rpart, you have to install the package first. rpartplot, also you have to install the package first. So let me run. Also, I have chapter 13, in-app purchase data. And what I'm going to do also, I'm going to change the buy as a factor, because now if you look at the structures, it's going to be a numeric. So I'm going to change it to factor. So run. I have my data. Look at the data. This is the buy. This is my response function, zeros, ones. So if you look at the buy, it's a numeric. After we change it, it becomes a factor. After that, we are going to partition the data. So let's partition the data as we did before. So I'm going to have 70% for the training and 30% for the validation. So I'm going to create the index first. So we have training and validation. We have 281. We have 119. After that, we are going to build the classification tree. And the question says, what are the predictor variable and the split value of the first split of the default classification tree? So to do this, we're going to use a function called rpart. Rpart is, this will help us to do the classification tree, or to develop a classification tree. And we can use the summary function to view the details about the default tree, because we are using cross-validation technique. And let's set the seed to be 1. So let's call it the default tree. rpart. My response is by all of the predictors. My training data, I'm gonna look at my training. The method is going to be classification method. So the tree using classification technique. If you run this, you'll see nothing, but you'll see on the environment we have something has been established there, which is the default tree. It's a list. You can look at the summary if you would like. Default tree. The summary is going to be long most of the time. So we have the function. We have number of predictors, or number of observations. Number of observations 281. And we have the CP. CP is, we call it the complexity parameter. This one controls the size of the tree. And we always looking for a smaller, no, they're not looking. If you look at for the smaller CPs always, if the CP is small, give you larger trees, okay, with more nodes. The end split is the number of the splits made in the tree. And this is, for example, 0. This is 1. This is 2. This is 3. So we have multiple trees here. It gives you the option of multiple trees, okay? The real error is the relative error. It's the proportion of the misclassified observations at each split relative to the total number of observations. We will not look at this guy. We will look at the last 2 columns. So we are going to look at the cross-validation error, which is the X error. This is the cross-validation error estimate. And this is exactly what is the performance of the model, the predictive performance of the model on the new data. And this is kind of the standard error, or the standard deviation of the cross-validation error. Also, if you look at the variable importance, it shows the importance of the variables in the model. So the most important variable is the income. The highest number, the better, or a greater importance. So the income is the most important, then the years, then the hours, etc. Okay. After that, we're going to see each node, information about each node. There's no need to look at all of them because it's going to be long now. But it's clear. You can just read it. It's very simple, very straightforward. It's not complicated to read each node. So we're going to skip this one and move and look at the tree. So how to view the tree? We're going to use a function called PRP. PRP. So it's going to be default. We're going to view the tree that we have built, which is the default tree. And we're going to specify the type to be 1. The type 1, all nodes except the leaf nodes are labeled in the tree diagram. So this is the meaning of number 1. Also, we are going to specify the extra one. Extra is going to be 1. So number of observations that fall into each node is displayed. You can change it to 0 and see what's going to happen. You can change these numbers. Also, I recommend always you change the numbers and see what happens. Even under true, change it to false and see, because this one put the number of cases under each decision node. So if you change it to false, you will not see them. So this is the tree we are getting right now. So the most important one is the income, right? And it's the first one. Is the first split. The first split occurs, or the income is the variable that takes the place of the first split. And the split value is 64. So without doing any split, what are the total number of buys and non-buys? 148, we have ones, 133 zeros right now. So that's why R placed 1 here, because it's the majority of the cases, because this number 148 is greater than 133, so the 1 is the winner or something. But after doing the first split, if the income less than 64, we're going to go left. So how many cases do we have zeros? 69. How many cases we have ones? Zeros. So you can immediately, and look, this is the terminal, by the way. This is a terminal node. So you can immediately say, if someone has an income less than 64, they have never made an in-app purchases. Or you can say, I will not consider this kind of segment because these people will not make or will not buy. So I can exclude, if you collect your data in the future, you can exclude, for instance, you can exclude the people who are making less than $64,000, right? But if you go to the right, if the income is greater than 64, we have another split. We have to look at the years now. If they have been playing games for less than 2 years, that means they will not make a purchase, or at least they have not make in a purchase, or we have 25 of them, which is the decision is going to be no or 0. If they have been playing for more than 2 years, we have to look at another split, which is years. If it's less than 5, we look at the hours, how many hours they play. If it's greater than 5, then we can say this is a terminal, again, node, that they will, the majority says 107, they will make a purchase. So the decision is 1 here. Look at this node, by the way. This is a pure node because all of the cases are 69 here, not here. We have nothing on ones. So all of them are zeros, okay? And so on. So this is the tree that built by R, which is the default tree. And the R part function uses the CP, which is the complexity parameter. This one. Oops, where is it? Let me hide this. This is the CP. So the R part uses complexity parameter to determine when to stop the growing, the tree. So if the cost of adding another split to the tree exceeds the value of the CP, then the tree growth will not continue. And the question is, what is the default value the R part uses for the CP? The default value is 0.01. So because it's not easy to know what is the best CP or what is the best value of the CP that produces or give you the best performing tree, so what we do normally, the best practice is to grow the full tree. Then after growing the full tree, we are going to look at the best pruned tree. So we just prune it, okay? We just prune it based on the cross-validation or based on the error that we are going to get, or the cross-validation error. So that's why now, so the first question, I don't know the first question, what are the predictor variable and the split value of the first split? So we can say the predictor variable was the income, and the split value is $64,000 to answer the part A. Okay, so we have to write down the answer, by the way. Now we have to build the full grown tree. Again, the full growing tree, we have to specify the CP to be 0. So let's call it the full tree. Because I'm going to develop or to grow a tree, so I'm going to use the R part again. By is my function. Training data. The method is still a classification. CP is 0. So the complexity parameter is going to be 0, which is the lowest. So it's going to be a large tree, as we said. Also, I'm going to add 2 more arguments. We have many arguments if you look at the function. I'm going to add the minimum split, which is 2. So give me the minimum number of observations that must exist in a node for any split to be attempted. So at least we have to have 2 observations in a node for the next split to be done. So I'm going to add the minimum bucket, which is, again, it's the minimum number of the observation in the terminal node. So we need to make sure that the terminal node contains at least some observations. Let's say this is 1. Okay. After building the tree, let's view it. PRP view the folder tree. You can again specify the type, the extra, and the under, which is true. Okay. If you have many observations and many variables, it's going to be a longer process. It takes time to process this, and it takes time to build the tree. So this is my biggest tree. Now we start to prune this one. Okay. So first, what we have to do to prune it, we are going to look at the CP values. We are going to look at the CP values, complex parameter, and this is associated with the smallest cross-validation error. We are going to look at this one. So I think we can use something called print CP. Yes, print CP folder tree. That just shows you the CPs. Okay. You can look at the summary. That's okay. I don't know if the summary shows you all of the CPs, but print CP shows you all of the CPs. Let me look, by the way, summary. But the summary is going to be very long because you have many nodes. No, I don't want to do this. So the CP now, look at, again, we talked about these, right? CP split, we have 0.5, we have 0.1, we have 0.0001, etc. Let's look at the minimum cross-validation error tree. Which one has the lowest cross or minimum error? Which one has a minimum error? Which is the minimum error tree. So we look at the minimum error tree. It seems that this is the one that has the minimum error tree. So the tree that has 2 splits, you add 1, you get 3 leaves or 3 terminal nodes. So number of the splits plus 1 give you number of terminal nodes. So this is 2. So we have 3 terminal nodes. So actually, if you look at this tree, this is the best, not the best to prune. This is the minimum error tree. The best to prune the tree is the one that is going to be within 1 standard deviation of this one. But it should be simpler than this one. It should be simpler. It should be better than this one. Okay. So if you add this number to the standard deviation, 1 standard error, if you find a tree within that range, it should be simpler. Simpler means I'm not looking for something more complicated. What does it mean? I'm not looking for something below this. The question is, are you going to get something above this one, which is the best pruned tree? How to know this? What you have to do is just adding this number to this number, which is the standard error. The standard error, you add it to the minimum error tree. Then you're going to get the tree within 1 standard deviation. Then you're going to look at up here. This or this. If you have something within the summation, then you're going to take it. If you have something greater than the summation, so it's beyond 1 standard deviation. It's higher than 1 standard deviation. So we will not take it. So there's 0.30. If you add 0.04 to this number, you're going to get 0.34. So 34%. 34%. The next simplest tree has an error of 48%, so it's still higher than. So the best minimum tree is actually the best pruned tree, is the same. Does that make sense? So this is it. It's just clear. So we have the best pruned tree is the minimum cross-validation tree. Okay. So to answer this, the best let's write something here. So the minimum 2 splits with CP equals, and we found none of simpler trees within 1 standard standard error of the minimum error tree, i.e. 0.30827 plus 0.04493 is equal to approximately equal 0.34 or something. Let me add them, by the way. Or yeah, I mean, let's say 3.5 approximately, okay? And this is still less than the previous simpler tree with an error of 0.48872. Okay, previous. Thus, the tree with two splits is also the best pruned tree. Does that make sense? So this is the best pruned tree. So what you have to do, just go back, prune it. Let me use another split here. Let me use, where is it? So we said we're gonna pruned tree. Oh, there's a function called a prune. Full tree, and I have to specify the CP value. We decided to have this tree. After that, we can look at that tree. Same arguments. Very simple. Two splits, 3 terminal nodes. If the income less than 64, don't bother. If the income greater than 64, focus on these people. Then look at the experience. How many years they have been playing. Less than 2 years, don't bother. So we are focusing on this segment. Nice information, nice kind of result. Let's see how good it is this guy. How good is the model, right? So let's create a confusion matrix now and see how good we are doing. Confusion matrix. So first, let's create the class, a predicted class. Okay. You can create a predicted class, or you can create a predicted probability, then change it to class. If you'd like to, we talked about this maybe many times. If you'd like to play with the cutoff values, if you'd like to change the cutoff values, so first you've got to create the predicted probability, then create a condition, then you classify them based on the condition, because the default one is 0.5, the cutoff value. So now I'm not going to change anything, so that's why I'm going to say predict. So that's why I'm going to create a class, just a class based on the default cutoff value. Pruned tree. Again, I'm going to apply this to the validation, the data that they have never seen. The type is a classification, just a class. Okay. So predicted class. So we have classified all of the validation set to buy, non-buy, to buy, non-buy. Then we are going to compare. What we have in the validation set already and what we have predicted for. So by creating the confusion matrix. Confusion matrix is a predicted class. The zeros are the ones that we give for the validation data. Also, we're going to look at the actual data, which is the validation at buy, or $buy. And we have to specify the positive because this is helpful when you do the sensitivity and specificity. So the positive value is 1, not the 0. Okay. Then we run this one. So what can we say here? We are using the default cutoff value, which is 0.0, which is 0.5, right? So the overall accuracy of the model is 77%, which is perfect, which is not perfect. I mean, I cannot say perfect or not perfect. We can say it seems good, okay? And the sensitivity is about 98%. Specificity is about 54%. Given that the classification tree would have an accuracy, which is the unknown information rate, which is 0.53, what does it mean, this one? It means that 53% of the observations belong to the majority class in our data set. This is the meaning of that one. Again, 53% of the observations belong to the majority in the data set. So what does this mean? It means if you were always to predict the majority class for every observation, you would achieve an accuracy of 53%. So we have a good database specifically for the sensitivity here, for classifying the positive values. So let's comment on this at the end. I mean, at the total or an overall view at the end. What if you'd like to change before we go to the charts, what if you'd like to change the cutoff value? As I said, to change the cutoff value, you have first to create a predicted probability. You have to get the probabilities values, prob values. We're going to do predict function as is. We're going to choose prune the tree for the validation, but for the type is going to be not class. Don't classify them. Just give me the probability, Because if you take the probability, by the way, let me copy this and show it to you here. It's going to give you the probability. We've done this many times, the probabilities. What is the probability that the first case will be having a 1, or it's 79%, and the rest is going to be none by, or has, or yes, will make up, will purchase or will not purchase. The second case, third case, etc. Based on the cutoff 0.5, the previous function, which is the one that contains the class, classified them. But maybe you'd like to create a confusion matrix. Let's create like a kind of sophisticated function here. So we're going to put comma validation by, right? This is technically what validation by. Then we're going to say positive is 1, right? But before that we need the positive. But before that we need the predicted classes, right? The predicted classes. To do this, we can put this inside a function, which is if else predicted probability. Let's look at the second column only. Second column, because we have two columns. Look at the predicted probability. I'm going to look at the second column. If the predicted probability is greater than, not 0.5, 0. Let's say 7, okay, then return 1, otherwise return 0. If you're not happy with this, I can cut this and create a function here and call it class, or predicted classes, predicted class. Not the previous one, because this is different classification now. I can give it that name. Also, I would like to change it to numeric or factor, as factor. I'm going to put it inside the factor. So now I can put inside here, the first argument is going to be the predicted classes. Now I change the cutoff value the way that I want. So there is no need to do this from the beginning, this and this. You can create this, then this one, then that one. And you can play with this one. You can change it to half, the default settings, greater than or equal half. So this argument is similar, these functions is similar to these two right now. But what makes this better, that you can change the cutoff value to other than half. So for instance, look at this. We should have the same numbers. But what if you change this to 0.7? Maybe you are planning to change the sensitivity and specificity, right? Nothing has been changed. Let's put 80%. This is 0, this becomes 1. So there's no point of doing all of the changes here. So you have to be careful. And I would suggest that we look at the ROC value, the ROC and AUC value, ROC chart, and we can tell. So this is one of the ways if you'd like to change the cutoff values. There's no need to do this right now. Okay, you can try this one, but in general you don't need to do this here. The decile, no, this is the decile. So let's now create the charts, decile charts and decile wise and cumulative lift and the ROC. Okay, so I'm not going to repeat these because we have done this before. Okay, so we need the probability. Let me cut. So I'm going to need this one, so I'm going to delete these. So I'm going to create the probability again because I need it for the gains table. I just forgot about this. To create the gains table, as we did before, I'm just going to change the by function to be numeric. So we do this trick as character, then as numeric, because we need the values to stay zeros, ones. Okay. Then we use the gains function to create the gain table. And it's nothing new. It's just the validation by, then the predicted probability. Then we create the tables. The table is needed because we need to create the cumulative lift chart. And again, I'm using the same arguments, the same functions we have used in Can and Naive Bayes. Everything is the same. Nothing has changed. Just make sure that you change the functions only. Validation that are signed by. Okay. So this is the, let me scroll this down. This is the lift curve. And it's very clear that the lift curve of the model lies above the diagonal line. And this is important. Maybe in some of the examples, maybe some of the projects or something, you're going to see this guy lie below or on the, or a little bit above this one. That doesn't seem a good sign. But this one, it's doing all right because this suggests that the classification tree performs better than the baseline model. This is the meaning of having your curve, lift curve above the baseline or the diagonal line. Okay. The baseline model is the random classifier, is the random. If you randomly assign the cases, this is the curve. So this curve is kind of able to identify larger percentage of the target classes, the customers who perform or who did in-app purchases, right? So in general, we see a good model in the decision or in the classification tree. What if we create decile-wise? Again, I'm using the same arguments, the same functions, but I change the validation $sign by. We have to change it everywhere you see it. We have a good kind of decile-wise lift, because look at the leftmost bar. It says that, or it suggests that by selecting, this is important, by selecting the top 74% of the validation cases with the highest predicted probability of belonging to the target class, which is number 1, the tree classify would identify 1.4 times as many target class cases as if the cases are randomly selected. So it's still doing better than the random selection. Okay. For the ROC curve, again, the ROC curve, we have the validation data assigned by the predicted probability, number 2, the second column. And we're going to look at the AUC value. If you run this, again, the model performs better than the baseline model in terms of sensitivity and specificity. The AUC value is 0.76, which is close. I mean, it's closer to 1, closer to the optimum model, right? Compared to the baseline model, which is 0.0, which is 0.5. The base model 0.5. The curve is above the baseline model, and this is across all of the cutoff values. These are across all of the cutoff values. So in general, what we can conclude that the performance measurements and the graphs, we can repeat what we said, before, suggests that the classification tree is effective in classifying the data. The lift curve of the model, it's above the diagonal line, right? So this suggests that the classification tree performs better than the baseline model, as we said. And the ROC is above the diagonal or the baseline model as well, right? So we have good numbers in general. So the tree is doing a good job in general. So I'm going to summarize this and write this down here. But before I do this, I'm going to, and this is important for me, and it's not, the whole thing is not about creating models. The whole thing is about interpreting models. The whole idea is interpreting models. It's not interpreting well and whether you decide you're going to use it or no, how good or bad it is. So this is important, super important, by the way. So let's do a score, because we have another worksheet, okay? So we are going to give them scores. We have some people, some predictor variables, then we're going to say these people are going to make a purchases or no, based on the model that we have built, the best pruned tree. Let's call it by score. Read Excel. It's chapter 13. Chapter 13, yes. XLSX. The sheet is in app purchase score. It's not found. I have to search and look at the name again. Score. Here we go. So after that, let's predicted. Let's look at the by score, by the way. By score. We have 2 observations with age, sex, income, years, hours of predicted card Facebook. We have to just to predict what's happening. Are these people, for example, I can look at this. Look at their income. For example, their income is greater than 64. Then we're going to look at, if you remember the tree, it says years. So the probability that this guy, he may make, purchase this one, no, because less than 2 years. But let's go back and do this using the tree. Class probability. Or let's actually add them. Let's add them. Add the values to the prop. Let's add it to the sheet, okay? Predict pruned tree by score type equals. Look at what we have added. We have added them here, and as we expected, look at this. So the first person, we said he's going to make a purchase. The second one, we said no, because he has been playing for less than 2 years, based on the best pruned tree. So to summarize, I'm going to write everything down here. Then let me pause and just summary write the summary of the findings. So this is the summary. We can use it, and yeah, that's it.